Today, we want to introduce the idea of a vector and learn about some math that goes with vectors. A vector is a quantity with not just magnitude, but also direction. A vector is a quantity that has magnitude and direction. The numbers that we've been dealing with up to this point, we could refer to as scalars. A scalar is just a magnitude. So all of our real numbers, those are scalars. A vector has magnitude and direction. We usually represent vectors with arrows. We usually use arrows to represent vectors. Because an arrow indicates a direction. Here's an arrow with the direction of, looks like 45 degrees above the horizontal. We'll use the length of the vector to indicate the magnitude of the vector. So the length of the arrow will indicate the magnitude, and the direction of the arrow will be the direction of the vector. So we see that the second vector is shorter than the first vector, but they're going in the same direction. As far as naming vectors goes, when we're typing, we use bold, but when we're writing, since we don't have bold, we just put a line over the top. Sometimes I put an entire arrow over the top. Eventually, I'm just going to get lazy and stick lines over the top. So here's a vector, and I want to name it. I call this vector V. And since I want to indicate a vector, I'll put an arrow over the top. So an arrow over the letter indicates a vector name. So here's a vector V, and this other vector can be vector U. But that's how we'll denote vectors from scalars. So scalar names will just be like our regular variable names. No arrow over the top. So scalars will not have arrows above, as usual, like normal. Notice that the vector v and the vector u are going in the same direction, both about 45 degrees above the horizontal, but vector v is twice as long as vector u. Other notations that we would, the notations that we've used before are still going to be in play. I want to say that v is twice as long as u. I will say that v is equal to 2u. Here's how I can say that v and u are going in the same direction, but v is twice as long as u. We could say that v is a scalar multiple of u. We could also say that u is a scalar multiple of v. Right now, I'm going to say v is a scalar multiple of u. But eventually, when we're all cool and we all know more, I'll just say v is a multiple. We'll drop the scalar part because we'll all know. We'll all be in the know. So I'm going to put it in parentheses. And so if I say something like v is a multiple of u, you'll know that I mean that v is a scalar multiple of u. If you know, you know. You can also say that u is a multiple of v. See, I'm already treating you like you know. I could say that u is 1/2 of v. They're scalar multiples of each other. This goes along with stuff that we've seen before. Think back to amplitude and period. Multiplying stretches stuff out. If I take v and multiply by 1/2, I squish its length to 1/2 of what it was before. If I take u and multiply it by 2, I stretch it out to twice the length it was before. Just like when we multiplied by 2, our amplitude on the after the trig function, our amplitude increased. This is one of the operations that we want to perform on vectors, scalar multiplication. And we can see what it does. Scalar multiplication of a vector stretches the vector or shrinks the vector. If we multiply by a -1, you can guess what's going to happen. So if I have a vector w, I'm going to make a flatter vector. I'm going to go out 3 and out 2 and up 1. So here's a vector w. If I multiply this vector by a negative scalar, we're just going to make the direction the opposite. You multiply by -1, that will change the direction of your vector. If you multiply by a negative, you change the direction to the opposite. So here I multiplied W by -1, -1, and it changed the direction, but notice that the length is the same. If I multiply W by -2, that'll change the direction because of the negative and stretch it out by 2 because of the 2. So I'm going to move the bottom, but it's going to go down 1 over 2, down 1 over 2. So here's a vector that will be -2W. This is one of those things that I could have opened up vectors with a quiz. I could say, here's a vector. What do you think 2 times this vector would be? And you would just like draw it twice as long. This is exactly what you guessed would have happened. It's always great in math class when what's supposed to happen is what you would have guessed anyway. Now that's always the best part of math class. So this is all an operation on vectors called scalar multiplication. So this is an operation that we'll call scalar multiplication, because what we're doing is multiplication by scalars. See the clever name we come up with? Notice, so what we're doing with scalar multiplication, we take a scalar, multiply by a vector, and come up with a vector. So this operation has scalar times vector equals vector. Next up, let's look at our other basic operation, which is vector addition. Our other base operation when we're dealing with vectors is vector addition. This is where we take a vector plus a vector and come up with another vector. This operation is going to have the form vector plus vector equals vector. So I'm going to have a vector. Here's a vector v. And I'm going to use a different vector u here are a couple of vectors that we want to add. The way we add vectors, we could do this visually. I'm going to pick a starting point. I'm going to draw one of the vectors, and I'm going to attach the second vector to the end of the first vector. So I'm going to draw the vector v, which is up 3 and right 1. Here's the vector v. At the end of v, I'm going to attach vector u. Vector u goes right 2 and down 1. So right 2 and down 1. And so the sum of those vectors is just connects the start of the first vector to the end of the second vector. Just like all addition has to be, vector addition is commutative. What if we had drawn u first and then attached v to the end of u? So notice that vector addition is commutative. If I had drawn the vector u first, which goes and v second, so from here go up 3 and right 1, we would still have the same resultant vector. V plus u would still be the same. The order that we draw, the order that we draw the vectors u plus v is the same as v plus u. Vector addition, like all addition, is commutative. The order doesn't matter. Not all things that we call multiplication are going to be commutative, which is it takes a while for us to find that. But addition, anything that we're going to call addition has to be commutative. It's one of the rules. We have something, some operation that isn't commutative, we don't get to call it addition. We got to call it. Any questions? Is everybody okay? Now, we can't be describing these vectors always with arrows. It takes up way too much space. Plus, they might be going in weirdo directions. So another way that we can describe vectors is with rise over run, but we separate it out to a run, comma, rise, and it looks like we're going to be writing coordinates. So we can't put it in parentheses. People might get confused. So we use fancy parentheses. So notice that this vector v, I started here at, I picked a point to start off with, and then from there I went to the right 1 unit and up 3 units. So I can list vector v as being 1, 3. I can have horizontal and vertical components. The vector u that I used in this example, just from some whatever starting points, goes 2 to the right and then down 1. So my horizontal component will be 2 and my vertical component will be -1. So a lot of times we like to describe vectors with horizontal and vertical components. And then to make sure that we're indicating a vector and it doesn't look like just a generic point, we put them in these pointy brackets. Now we got, once we're describing vectors with these horizontal and vertical components, we refer to those as components. Sometimes you'll hear me say coordinates because sometimes I mess up my words and they both start with the co, but they are components when we're talking about a vector, a horizontal and vertical component. We got to do our operations, but with horizontal and vertical components. We have vectors described with components. Fortunately, it's exactly what you think it would be. So if I want to add the vectors v and u, the vector v is 1, 3, and the vector u is 2, -1. So if I want to add these components, I add the horizontal components, 1 plus 2 is 3, and add the vertical components, 3 minus 1 is 2. Now, if we look over here to this v plus u, there's our 3 horizontal components, and there's our 2 vertical components. Vector addition in components, we just add the corresponding components, which is exactly what we would have guessed. It's great when math is just like what you would have guessed. Add the corresponding components. The same is true for scalar multiplication. The vector w that I drew up here has a horizontal component of 2 and a vertical component of 1. So this vector w is 2, 1. If I want to figure out -2 times w, I'll just multiply those 2 components by -2. So -2w is just going to be -2 times 2, 1. So if I look at that starting point of the -2w, I drop down 2, 1, 2, and go to the left 4, 1, 2, 3, 4. Just like we would have guessed. Question? So one of the ways we want to describe vectors is with horizontal and vertical components. Sometimes we have a different set of information about our vectors. So sometimes we will want to know, we have a vector described with a magnitude and an angle. So rather than components, we have a magnitude and an angle. Sometimes vectors are described with a magnitude and an angle. Sometimes we'll describe a vector with a magnitude and an angle. The angle, the way we use an angle to describe a direction, there are multiple ways of just using an angle to describe a direction. We could be using an angle in standard position, so degrees above the horizontal. So when we talk about an angle in describing a vector, it could be in standard position. Which is above the horizontal, degrees above the horizontal, or degrees above the x-axis. Degrees from the positive x-axis, with counterclockwise being the positive direction. This would be degrees above the horizontal. This is the same standard position that we had before. We might describe degrees above the horizontal as an angle of elevation. So if we have an object above the horizontal, we can describe the angle of elevation to that object. So we just connect where we're standing and looking at the object. This would be our angle of elevation. So we could be describing a vector with a magnitude and an angle, a magnitude and a direction. And the direction comes in the form of an angle. Given this information, we might want to break our vector into horizontal and vertical components. So we can use this description to find horizontal and vertical components. So here I'm going to describe the vector v with a magnitude and a direction. The magnitude of v, denoted the magnitude of v, is going to be 12, and it's going to make an angle of 30 degrees at the horizontal. If we want to indicate the magnitude of a vector, we'll write the vector in absolute value signs, or like these fancy double absolute value signs for the norm of our vector. So those double absolute value signs indicate the length of a vector or the magnitude of a vector. I know we're trying to describe vectors with all these numbers, so we don't have to draw pictures, but let's draw pictures anyway so we can see how they're related. So I'm going to draw a vector v. It's going to be 12 units long and form a 30-degree angle with the horizontal. I'm going to draw on my horizontal for reference. I'm going to make an angle of 30 degrees and put a length of 12 at that 30-degree angle. We might want to describe v with its horizontal and vertical components. So what we're going to do is try to break v into two vectors, write v as the sum of two vectors, one horizontal and one vertical. Now I can write V as a horizontal component plus the vertical component. This is breaking a vector into components. Our notation is, I should have chosen V, but oh well, I'm stuck with it now. Sometimes for the vertical component, I'll say the vector V, and then I use a subscript of V, and the horizontal component will be V sub H. And you can see what we built here is a right triangle. And I want to know I have a hypotenuse and I have an angle, and I want to know the side opposite, and I want to know the side adjacent. So the side opposite is going to be the magnitude of the V vertical component. If we divide this by the hypotenuse, this will be the sine of the angle. So the magnitude of the vertical component will just be the 12 times the sine of 30. We're just solving a triangle now, a right triangle. We have an angle, we have got the hypotenuse. We'll use sine to find the side opposite, and then we'll use cosine to find the side adjacent. So cosine, sine of 30 is a half. So cosine of 30 is √3/2. 12 divided by 2 is 6. So we'll get 6 times the square root of 3. So I could write the vector V, which has a length of 12 at an angle of 30 degrees above the horizontal, with the components. The horizontal component is 12 cosine of 30, or 6√3. And the vertical component is just 6. One way we can imagine these horizontal and vertical components is two people pulling something along. One person is walking horizontally, and they're dragging at 6 times the square root of 3, so 6 times 1.7. Let's just call it 6 times the square root of 3. And the other person is dragging vertically at a speed of 6. We could see that the resultant vector, this will result in the object moving at an angle of 30 with the horizontal at a speed of 12. So that's how the two vectors will interact. It's really weird that two tugboats will be trying to drag something like at 90-degree angles like this. I mean, if I saw that happening, I mean, well, that's an awesome math problem, guys, but that's really inefficient. And then the tugboat operators will be like, oh, well, we took a trig class and everything got broken down into horizontal and vertical components, so there we are. I guess more appropriately, let's suppose that the horizontal component is the tugboat and the vertical component would be the current that we're trying to drag this thing through. So if the tugboat just goes along the horizontal perpendicular to the current, then the current is going to push the tugboat at this 30-degree angle. How's everybody okay? It looks very sad. It'll look like this. Unless you're wearing a mask, in which case you look like this. Unless you're online, in which case you just look like, you know, your name. That would have been a great Halloween costume. Just like in-person Zoom, you just get a big black rectangle of cardboard with your name written on it in white on the front, and just like carry that around. Well, what are you? This is me in a Zoom meeting. Actually, if people ask, what are you? You don't say anything because you turn the camera off clearly because you're off making yourself coffee because you're at home. Do you know what I mean? So that's that. Okay, next year, I don't know if it'll be as effective. But there'll probably be some other disease. So we'll be back on Zoom like all the time. That'll be my costume. So next year for Halloween, now in November, I get my Halloween costume for this year. So that's what it's going to be. I'm just going to carry that sign around in front of me. It's going to have my name on it, and I'm just going to ignore everybody. That'll be the important part. Or actually, I'll ignore people and then just say random shit. And we're going along. So I'll need a recording of my dog barking. And then I'll have to tell myself that I'm not muted. So I'll be like walking around, someone say, what's your costume? And I ignore them. But later on, when I'm further down the hall, I'll like say, hey, is this spoon clean? No? Oh, okay. Oh, wait, I'm not muted. And then I'll stop talking. Or I'll just be standing there and then I'll play a recording of my dog barking. Like I'll be saying, oh, hi, how's it going? Oh, hang on. And then turn it off. And then just walk away from the person because oh, now I'm muted and the camera's off. You know what I mean? Did anybody do that? I can't be the first person to fucking think of that. I'm not creative. Maybe I am creative. I did have shit timing. But no one did that. Like I'm not on social media. So there was someone on social media like this year or last year or a couple years ago when we first started using Zoom all the time in 2020. Someone's like, oh, no, this is my costume. I'm on Zoom. Yeah, well, there you go. You get that one for free. That's going to do it for today. That's going to do it for this week. We'll come back and talk more about dealing with vectors on Tuesday. Everybody have a good weekend. Enjoy the holiday, and thanks for playing.